Hi everyone, this is Avital Breverman from the Hydrologic Engineering Center. This video is a recording of a webinar that took place on March 26, 2024. In this video, you will hear from 3 members of the HMS team, Mike Bartels, Lauren Coe, and Melissa Micah, about new meteorologic model methods in HMS versions 4.11 and 4.12. Enjoy and happy modeling. We're right at the top of the hour, so we're going to get started. Good morning or good afternoon, depending on where you're sitting. Thank you for joining us for our second HMS Quarterly Webinar of fiscal year 2024. My name is Avital Breverman. I'm part of the HMS team, and I will be hosting this webinar today. In today's webinar, you will hear from 3 other HMS team members, Mike Bartels, Lauren Coe, and Melissa Micah, and they will present on new meteorologic modeling methods in versions 4.11 and 4.12. Before I turn it over to the presenters, I just want to go over some logistics. You may have noticed that everyone is muted to minimize disruptions, but you are welcome and encouraged to put questions in the chat box throughout the presentation. Our presenters will either reply to your questions via the chat box or at the end of the presentation. We'll have about 5 to 10 minutes set aside for questions, and if we don't get to yours, please send us an email after the fact. This webinar is being recorded, and we will post it to our website and YouTube later this week. And I just want to show you where you can access our webinars in case you haven't seen that before. So I'm on the HEC's website under HEC-HMS, and if I go to training materials, there's a link for webinars, and that'll open up this page where we have all of our quarterly webinars, as well as other presentations that HMS team members have presented, and links to our YouTube channel. All right, I'm going to stop presenting, hand it over to Melissa, and I'll be back at the end for questions.
All right, thanks for the introduction, Avital. Thanks for everyone for tuning in today. My name's Melissa. I'm going to kick things off for us. So today we're here to talk about some of the new meteorologic methods that were added in HMS versions 4.11 and 4.12. 4.12 is currently in beta. We have beta 6 available on the website, and we're planning to fully release 4.12 imminently, very soon. Next slide, please. So in this webinar, we're going to do a quick overview of all available MET models in HMS, and we'll discuss our motivations for adding these new methods, how do they benefit you, and how they can be used. Then Lauren and Mike are going to take over and go over each of the new methods in more detail, followed by a quick demonstration. And then we'll wrap up with some examples of how these methods can be applied in practice, with time for questions at the end. And again, please feel free to use the chat to ask your questions. Next slide, please. In HMS, there's a few ways you can configure your MET model. The existing methods are shown here in black, and the newly added methods are highlighted in red. The first method is shown in the top figure, which is point or specified, where a time series gauge is assigned to each subbasin. Then we have gridded methods, which apply grids such as temperature, precipitation, wind speed, etc., and inherently handle the spatial and temporal patterns. Interpolated methods are a sort of combination of the point and grid methods where we interpolate spatially from point gauges. Some of you may remember or may have used the tool Gauge Interp. That has been integrated into HMS, and you can now do that virtually for all types of meteorologic data. So that's the interpolated method. And then what we have we call computed methods, which rely on various equations and input data to calculate the variables. So the Hammond method is one example of a computed method, which is calculating evapotranspiration using temperature data. So as of version 4.11, we have added a few new methods. We're calling those simple methods. These are computed methods that require fewer inputs, and they also make more generalized estimates. And then as of version 4.12, we have a new method called MetSim, which has methods for both precipitation and for temperature. And in short, MetSim is a method for disaggregating daily time series into sub-daily data. So each of those we're going to go into more detail in the rest of this presentation. So what is the purpose of adding these new methods The real world is super complex, and we do have a lot of simplification in order to model it. So if you look at this energy mass balance figure on the right, there are processes that we're trying to represent in our models. So there's a lot of these processes, but it would be very computationally and data intensive if we did not do any simplification at all. So while we have several physically based land surface processes that we can model, they require a lot of boundary conditions and input data that we don't always have available. The availability of data has gotten much better over the years, but especially for like historical events way in the past, this can be really hard to get. Or equally difficult to get data for future events, like if you're trying to run a quantitative climate change study. And even if you do have the data available, is it going to be at a reasonable temporal scale? So there's a lot of data sets that go back to the 1800s, but they might only be at a monthly scale. So the goal is to be able to infer these harder to get boundary condition data as long as we have precipitation and temperature data, which is generally more available than other data types. So let's talk about some of those data. There's a ton of gridded temperature and precipitation data sources that are available for both historical and future time periods. But it's important to note that gridded precipitation and temperature data sources are often provided at a daily time step. A couple of these common data sources are LIVNA and AORC. There's one LIVNA unsplit data source that is provided at a daily time step from 1915 to 2018. So that's over 100 years of coverage on the LIVNA data set. And then AORC is one of the most trustworthy data sets that has an hourly resolution, but it only covers 1979 to present day. So if we can use these precipitation and or temperature data to infer these other boundary conditions like relative humidity, we can use physically based land surface methods for many more time periods and locations throughout the world. And this is pretty much how every single hydrologic quantitative climate change study is performed at a reasonable spatial resolution. Downscaled long-wave radiation, for example, boundary conditions are not provided for 100 plus years into the future. They're inferred from other boundary conditions, which is what we're trying to do here with our simplified methods. And additionally, we can model this data much better if we take the daily data and disaggregate it into subdaily, which is the purpose of adding MetSim. So I'm going to pass it over to Lauren to talk more about these new simple methods.
Okay, great. Thanks, Melissa. So Lauren here, we're going to talk through some of the simple methods. Just building off of what Melissa said, what we're after here is how we can use things that are typically a part of our model: temperature, elevation, your location on the Earth, precipitation, and how we can use those to infer things like short, long wave radiation, pressure, and humidity, those things that drive the energy balance of those land-based surface processes. Next slide. Okay, so starting off with kind of our simple shortwave method. So reduce solar constant shortwave. So where this is needed, a shortwave radiation method is required for, as I said, the energy balance, evapotranspiration, and snowmelt methods. This and a few others that you'll see come from the Tennessee Valley Authority 1972 paper, as well as Mike Fulham's 2015 paper. The basis of this method is that we have a solar constant, which is the solar radiation at a given point on Earth, at a given latitude, for a given elevation, on a given day of the year, okay? What we're doing is we're using terms in, HMS is using terms to reduce that equation or reduce that solar constant based on, okay, how much farther we are from the Earth, or how much farther your point on Earth is from the sun, atmospheric scattering based on elevation, the slope and aspect of the terrain, and how the sun is, basically the solar declination, how the shortwave, how the solar radiation rays are hitting your point on Earth based on the day of the year. Okay, so those are all things readily available within your model. And you can see what it looks like in HMS is just these really simple drop-down methods. And so there's nothing for you to parameterize there. It's just showing you what method it's based on, and that'll all be pre-filled out for you. One thing to note here is that while you don't necessarily need to have a georeference model with terrain, if you don't put that kind of information in, or if your model is not georeferenced with the underlying terrain, it's going to assume that it's at the equator at sea level. So definitely more meaningful if you have that information within your model. And this and the rest of the simple methods that we'll talk about today all work with both lumped and gridded subbasins. So next slide. So if we take a look here, we can kind of see how our solar radiation or how our shortwave radiation method is doing compared to our observed data. So obviously observed is in the blue and solar in our modeled is in the red. And you can see it's doing a good job of capturing the overall shape, what you would expect for somewhere in North America. Obviously our solar radiation is peaking in the summer, and you have your you have the dips in the wintertime. And if we look at the graph on the right, it's just a zoomed in portion. When you take a look at where you're seeing these discrepancies between the modeled and the observed, that is most likely explained away with some of the terms that aren't yet captured within HMS, things like cloud coverage. That is not a term that HMS accounts for, so that's going to account for some of the discrepancy. But overall, it's doing a nice job of generalizing the shape. Next slide. Okay, so next we're going to talk about long-wave radiation. And so this simplified method is a Stefan Boltzmann Longwave method. Again, you need a long-wave radiation method for energy balance methods within HMS. And for this method of long-wave radiation, this does require both air temperature and relative humidity to be defined within your MET model. Those are typically readily available. And the reason for that being that the temperature and relative humidity are used within the atmospheric emissivity and saturation vapor pressure terms. But similar to the shortwave radiation method, if you look at how this is parameterized within HMS for the user, you simply have these drop-down methods. There's one method for atmospheric emissivity, and then I believe there are two for saturation vapor pressure. And all you need to do is select a method for each of those. So as I said, it relates to air temperature and relative humidity. We're going to talk about a simplified relative humidity method as well. So if I know that's not necessarily always readily available, but temperature should be. And so this again works for lumped and gridded subbasins. Next slide. Okay, so now we're going to take a look to how this does against the observed. So we have our red modeled method versus the observed. It's doing a pretty good job of matching the Stefan Boltzmann law. The premise is that the long wave radiation is it's proportional to temperature to the fourth. So it's very tied to the temperature. And you could see that obviously, as you'd expect, it's peaking in the summer months, right along with what you imagine humidity and temperature are doing during those times. Next slide. Okay, so now we'll look at our simplified pressure method. So again, you also need a pressure method for these energy balance methods within HMS. And so this is one that it does require some actual parameterization from the modeler, but it's fairly simple. So what this method's doing is that it is estimating atmospheric pressure using the elevation of your subbasin or grid cell. So the user simply has to specify a lapse rate, meaning how much, well, what you're specifying is how much temperature is decreasing per 1,000 feet or 1,000 meters, if you're in metric. And that is obviously tied temperature and pressure decrease right along as you go up in elevation. So 1 lapse rate is given per subbasin, and again, it'll work for both lumped and gridded subbasins. So for this case, because you are putting in a value for the parameter, you can take a look if you have observed pressure data at some point within your model domain. You can vary that lapse rate and try to reproduce the atmospheric pressure if it's available. If not, there are standard values, like for degrees Fahrenheit per 1,000 feet, the minus 2.8 is a standard value that can be used. And so what this produces is a constant time series, basically, of atmospheric pressures. And I should say what it's doing is it's taking pressure at sea level, and then it's reducing it from there based on the elevation. So again, this is one where highly recommended that you're using a georeference based model with terrain, so that it's not just taking it at sea level, and it's actually varying with your terrain of your model. Next slide. So here, the observed is in blue. This is really zoomed in on the y-axis, but you can see that if we're varying between 65 or so, 65.5 up to 69, what barometric pressure method is giving us is maybe right about 67. So it's doing a good job of going right through the middle of our observed data, and that is a good approximation, especially for something like a continuous simulation. Next slide. Okay, so next up is our dew point method, our relative humidity method. So this is a precipitation index humidity, and it is, well, let me first say this, that you do need a relative humidity method, again, for the energy balance, evapotranspiration, and snowmelt methods. I know I'm saying that over and over again, but for the relative humidity, that's also needed for the Stefan Boltzmann Longwave. So if you remember back, we used that relative humidity term to get the air emissivity in that. So this is kind of referring back to what I was saying, kind of the simple method to get around needing the relative humidity term there. So precipitation index is kind of exactly as it sounds. You're using a precipitation threshold to define what the humidity is assigned for that time step. So you define a wet humidity or a dry humidity, and your precipitation rate determines if it's wet or dry. So if you have a precipitation rate of 1 millimeter or 1/4 inch per day, if it's above that, it's assigned the wet humidity. Below, it's assigned the dry. So again, I would say that for this one, parameterizing is pretty simple. Obviously, you actually have to put parameters in, but something like 1/4 inch per day, your wet humidity at 100%, and your dry humidity, if you have any relative humidity data available, I'm going to show you on the next slide that you can kind of adjust that dry humidity to better hit the observed. Otherwise, I think this probably provides some good numbers to start with. And so what this produces is a binary time series. It's either going to be 100 or 30 in this case, but you're going to have a wet humidity or a dry humidity, and it's just going to fluctuate between those. So if we go to the next slide, we can see how that does. So yeah, you can see here, obviously, when it's raining, or when it's determined to be a wet day, it's putting it right at 100. And this is probably an example of maybe if you had this data, you might decide to bring that up a little bit from the 30%. Maybe like 40% is a better approximation. But either way, you can see it's kind of fluctuating right along with the data and giving a good approximation with our observed. Next slide. Excuse me. So the last thing I wanted to plug is the technical reference manual. that we have here. So we have this on our Confluence page. There's a link here in the slides, but you've probably looked at the user's manual, but if you haven't looked at the tech reference manual, it does a good job of providing the different methods and the underlying mathematical equations and assumptions. Especially when you're looking at new methods, I think it's a good idea to take a look at those, because if you go back to something like the shortwave radiation method, if you see those discrepancies between observed data, if you go here, the reference manual is going to tell you, okay, well, HMS isn't accounting for these terms, you know, and this, so in this like particular release. So it can just help you like be better informed with the method you're using. It also has some great guidance on estimating parameters and selecting like an appropriate method for your given application. So that's just a plug for that. And with that, I'll turn it over to Mike to talk about the MetSim methods.
Thank you, Lauren. Appreciate it. So like I said, or well, like Lauren said, I'm going to talk about the MetSim methods. Before I do that, I want to talk briefly, really like higher level stuff. Why are we adding all of these methods? Like Melissa had mentioned earlier, we're doing this so we can open up modeling to more time periods and in more locations, and also open up, roughly better speaking, improved modeling methods as well to additional time periods. If you've ever tried to simulate the 1927 flood along the Mississippi River, the March 1936 flood in the Northeast, the January 1964 flood along the West Coast, you're likely not finding gridded boundary condition information for that, right? You want to use grids. Gauges are hard to use because it's hard to go from point to space, right? When we do have these boundary conditions, they're typically in a daily time step as well, which also limits their applicability to smaller modeling domains. If you've ever tried to use daily boundary conditions over a modeling domain of like 50 square miles, it usually doesn't work too well. All of these methods are meant to allow you to simulate these time periods and also use these higher order approximations more easily. We want to get you to the modeling faster and have to worry less about data processing, where to get all this information, which stuff is appropriate, how to project this stuff, how to format it for use within HMS, so on and so forth. We want to make the stuff easier for you and get you modeling and simulating stuff faster. That's what we're really after here. In particular, for the MetSim methods, you know, we run into these problems where it's like, I got daily average time series. This may be for a more recent period, but imagine this was in like, you know, the 30s or something like that. We have daily precipitation accumulations and daily average temperatures. I can use them, but my model results are kind of junky from that. Time and time again, we find that predicted runoff, shown in blue over on this side, is way small compared to the observed, shown in black over here. When we uniformly disaggregate stuff in time, say we wanted to simulate this at a 1 hour time step, we take this daily precipitation accumulation, say like 0.2 inches, and we divide it by 24 if we wanted to simulate that over an hourly time step. That's a really, really small precipitation rate, right? Which is likely infiltrated by any reasonable parameterization in your infiltration or loss methods. We infiltrate everything. That's why your computed results are typically biased low. This has been shown time and time again, and this is really true for small modeling domains. The bigger you get, you know, towards a continental scale approximation, maybe disaggregating in time isn't so bad, but for smaller modeling domains, say in the 1,000 square miles or tens of thousands of square mile range, anything smaller than that, you got to do something better than this. That's why I give this a frowny face. That's not good, right? You can do better than that. Many of you may be familiar with the term MetSim, but those that aren't, it's an open source library, Python library in particular, that both simulates and disaggregates boundary conditions from daily time steps into sub-daily time steps. So it's commonly used as the meteorologic preprocessor to the VIC model, or the variable infiltration capacity model, which is used a lot in quantitative climate change assessments. It's been documented in this Bennett et al. 2020 paper. So if you want some reading on that, and I nabbed this figure from that, essentially what we're taking right here is daily min and max temperatures and interpreting better sub-daily inputs, taking daily precipitation inputs and then interpreting better sub-daily precipitation inputs for your modeling domain. We integrated those precipitation and temperature disaggregation components into HMS for you to use natively within HMS and get the same results that you would if you were to use MetSim standalone. First up, we're going to talk about the precipitation disaggregation method, or the MetSim precip method. This is based upon the Petrie method, which stands for precipitation isosceles triangle. Essentially, take this red daily precipitation input, which in the past we uniformly disaggregated over a day, now put it into a triangle with two equal sides, right? That's essentially what an isosceles triangle is. You tell me how big the triangle's base width is. So for how many hours or how many time steps in the day you want that to be split, and also where do you want me to put this triangle within the day, right? It's inherently a grid method, so please don't use this in a lump basis because we'll just uniformly do it. But yeah, use it to its full capabilities in a gridded method, please. The required inputs for this one are daily precipitation accumulations, so gridded daily precipitation accumulations that you select here at the top. And a temporal disaggregation and storm characteristics method. For right now, there's only one temporal disaggregation method, but we could add additional ones in the future as people get more and more interested in this. The storm characteristics method allow you to specify the two other parameters, which are storm duration. Again, that's the base width of the triangle, and the time to peak of when that's placed within the day. You have three different options for that. First one, just give me scalar values that are constant throughout the entire time period. The other one is annual pattern, so you can specify how you want these values to change throughout the year and then repeat in future years using parameter value patterns. If you're not familiar with that, I'll demo that in a second. You can also use grids. It's really, really nice. When this method was rolled out in this 2019 paper, they also developed gridded data sets for storm duration and storm time to peak for you to use. I included a link here where you can actually go and grab them. I've formatted them for you to use. And they look like this. There's 24 grids, two parameters, right? And they're monthly, right? So I have a grid for January, February, March, blah, 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 the whole way to the end of the year. You can sample from them to produce these patterns, right? And they're supposed to be applied as kind of a stepped function. We can talk about that if you guys would like to use it another way. I kind of would like to smoothly interpret those, but this was their intended usage. You sample from them as a pattern. The nice thing about the patterns or the parameter value patterns is they repeat. So I can simulate 100,000 years into the future, and I don't need to specify 100,000 grids. I just use the same pattern, and no matter what time we're simulating, I can always pull from this pattern and go. All right, now we'll talk about temperature. This is based upon an earlier paper from 2013, so I've included the link there if you'd like some background reading. And what we do in this is we interpret sub-daily temperatures using a spline fit. As long as you tell me what's the previous day's max temperature, the current day's min-max temperature, and the next day minimum temperature, I can figure out sub-daily temperatures and smoothly interpret from one point to another. Let's say we're on the 8th of February. As long as I know what the previous day's maximum temperature is, the current day's minimum temperature, the current day's maximum temperature, and the next day's minimum temperature, I can draw a smooth line between all these points. And I can also step forward in time and get the exact same values for the previous day so I don't overlap, or I do overlap perfectly and I don't overwrite anything that's bad. So you have to take two assumptions into consideration here, that the minimum temperature occurs at solar sunrise. So as the sun is rising, that's typically the coldest point in the day. And also that the minimum temperature occurs before the maximum temperature in a day. This is also a gridded method because we need to figure out where you are in the world to compute the solar sunrise, right? So for every single grid cell, I can figure out where you are in the world, where the Earth is with relation to the sun. Are you actually shaded or not too? I can take that all into account, and I can figure out for you when is the sun actually going to rise on that specific grid cell to compute a temperature, a minimum temperature for you. The required inputs for this method are daily minimum temperature grids and daily maximum temperature grids. That's really, really common. You can find a lot of those out there as well. Talked a little bit about the LIVNA data set. I'll demo that in the second one. I like using that quite a bit, but there's others, like PRISM. It's a really common one as well. And you also need to tell me when is the max temperature going to occur. That needs to be specified in minutes, somewhere between 0 and 1440. So in this case, I specified 960. That corresponds to 4 p.m. in the afternoon, which is a pretty common maximum temperature, especially in like the summer months in the West. but you can specify that as you would like to see. All right, I'm going to demo for a sec. So recently completed a tutorial and guide out there. If you guys don't know where this is, this eye-looking watershed, which is a really unique shape, we are near Lake Tahoe. So this is the Upper Truckee River, which is located here in California. Lake Tahoe is right here. The Upper Truckee River is right here. It flows into the Lake Tahoe itself from the south and passes through South Lake Tahoe. You guys know Tommy Brower lives right over here. I know there's a bunch of other people that live close, but I always want to give a shout out to Tommy. He lives in a beautiful area. Check out this tutorial and guide when you get a chance, because what I do in this tutorial is I set up a whole bunch of different computes for you. Typically, what we're used to seeing is something that looks like this. If I take daily precipitation inputs and I simulate them without disaggregating, or if I disaggregate uniformly in time, I end up with really junky results. Not only am I underrepresenting extreme discharges or flood events, I also push everything later on in the season because I don't warm the snowpack appropriately. But this isn't a phenomenon that's just limited to snow accumulation and melt scenarios. You'll also see this elsewhere, even in non-snow dominated watersheds. You'll see that. I can do a better job of that. Specifically, if I use these new MetSim methods, I can simulate much better the typical runoff response. So let's say we'll look at like February 86. I can get this peak to align a whole lot better. These are daily inputs, a whole lot better with what we actually would have expected to see. If I look at another time period, say like January 97, I can look at that as well. I get a much more reasonable response. So for instance, I think the peak was like 5,500 CFS this time period, which is way better than what you get with daily inputs as well. Now, I know what you're probably saying, it's like really difficult to ascertain model accuracy over long time periods, especially when we're using daily inputs in terms of precipitation and temperature, but there is a tool for that. So everybody go check out Tommy's continuous simulation calibration app. And what I can do with that is in this app, I specify where I want to look, what DSS file I want to pull from, what paths I want to pull from. So in this case, I want to get the flow at South Lake Tahoe, and I want to compare that against the South Lake Tahoe flow observed time series. I want to use this time window, essentially water year 1971 through 2011, and I want to aggregate everything to a one-day time step, right? So my inputs are, my observed data is in daily time step, but my computed is in hourly. Don't compare those two natively as they are because you won't get appropriate statistical metrics. But once I convert to a daily time step, I can actually compute Nash cyclic efficiency, RSR, P-bias, R-squared. I can also compute monthly average time series, so essentially flow duration time series, which are really nice. And the reason I want to show you this is how bad the model performs when you don't disaggregate the stuff in time or use a reasonable approximation. So this is with uniform temporal disaggregation, which is really bad. If I disaggregate using these new MetSim methods, using a reasonable approximation of when precipitation occurs throughout the day, and also how temperature changes throughout the day, I get much better results as well. In this tutorial, we also talk about other things that you can look at. So line of best fit plots, also flow frequency plots. The really cool thing that I can do with this then, now that I have this calibrated model, I can simulate the entire time period, right? So 1915 through current using the LibNA data set. Right now I have 57 more years of runoff results than there are actual gauge results at this location. I can make a flow frequency curve with way more information from that information content than I could if I were to just use the observed data. I can mix the two together as well. I can produce frequency curves that have many more observations in it than you would if you just used the observed data itself. I can also more readily assess, hey, if I were to put some sort of a structure right here to divert water, impound water, if I were to assess land use changes, if I were to look at all sorts of myriad with and without project conditions, now I have a model that I can accurately assess all of those potential changes. And I can get a much better sense of whether that project works or not. the LIVNA data sets, the really, really nice thing, these are available for the entire continental United States, right? So if you have a model in the continental United States, you can do this exact same thing from 1915 through current. There are other gridded boundary conditions available as well that go further back in time. Some of them suffer from spatial discretization issues, but this is available throughout the entire continental United States. So if you have a continuous simulation model, or if you have available time to up your model to use continuous simulation techniques, you can do this too. You can generate flow frequency curves like this as well for anywhere in the continental United States and do it much more accurately than you could as well in the past. All right, that's all I wanted to show for the demo. Thank you guys for the time. Let me kick it back over to Melissa.
All right, thanks, Mike. Do you mind pulling the presentation up again?
I stopped sharing. My bad. There we go.
Okay, so I'm going to share with you some of the applications of these new methods. These are just two examples. There's many more situations where you could use the new methods, the simple methods, and MetSim. Next slide. So the first way you can apply these methods is in continuous simulation, which Mike just gave us a really nice example of in his demonstration. As we mentioned earlier, there's many sources of daily gridded data for precipitation and for temperature. So this means if you have a model that has been calibrated for continuous simulation, you can simulate 100 or more years of rainfall runoff anywhere in continental US with better accuracy, since you can model more of these energy mass balance processes with fewer data input requirements, and because we can disaggregate that daily data to sub-daily. And as Mike showed, that typically produces much better results than disaggregating with a constant. This also makes calibration easier if you have fewer parameters that you need to calibrate to. So these long-term simulations can be used to produce frequency curves, as Mike explained, which you could use to assess with and without project conditions. So if you create a basin model of your with and without project and run the continuous simulation for the full time period, you can develop frequency curves for those situations. We have a tutorial on the HMS website, which Mike mentioned, using the MetSim, precip, and temperature methods. So that's linked here in the presentation. Definitely do be sure to check that out. That runs through the example that Mike just showed. And then we also have a tutorial for calibrating a continuous simulation model. So if you haven't done one of those before, or if you don't currently have a calibrated model for continuous simulation, that's a good tutorial to check out as well. Another method that you can use these methods for is quantitative climate change studies. Since the availability of data for the future is very limited, we have to rely on these simplified methods and temporal disaggregation. And typically you will only have daily spatially downscaled data to use for climate change studies. So these new methods are really opening the door to performing these types of studies. One example of a type of data set is the CMET5 climate projection. It's one source of daily gridded data that has both temperature and precipitation, which, as we mentioned, are two of the important data sets that we can use to infer the other boundary conditions. And that has data available from 1850 to 2300. So the example shown here on the right is from SuccessSTAM, and they created a MET model for each of the CMET5 scenarios. And linked there below is the tutorial that runs through performing these climate model data sets using CMET5. Next slide. So just to recap, there's many different types of MET models available within HMS. We added 2 new types of MET models in 4.11 and in 4.12, which is letting us use longer and more accurate simulations by using these simplified methods, as well as the MetSim disaggregation. These new methods, combined with gridded boundary condition data sets that you can readily get for CONUS for over 100 years worth of data allows you to model longer historical periods, future periods, for any location within CONUS. These can also be used to estimate runoff for future climate scenarios. So there's a lot of opportunities for using these new methods. We hope you find them useful. We hope you check out our tutorials as well.
All right, I would be remiss if I didn't thank a bunch of people as well as showing you guys some of these new things. Major shout outs to the Mississippi River Geomorphology and Potamology program for actually funding a lot of these enhancements. They wanted to see the MetSim methods incorporated within HMS. Sean Smith's state agency Science and Engineering Technology program, the SET program, provided a lot of funding for bug fixes and stuff like that. Angela Duran's group in the Northwestern Division Columbia River offices funded a lot of the simple methods, as well as the Arid Regions Work Unit, was led up by Ian Floyd and Travis Dahl. Major shout out to them. Mike Fulham, though, did help us actually implement a lot of these methods. He wrote a lot of the code. So if you guys are interested in working with us and adding new capabilities that you or your district are interested in funding, let us know. Also want to give a shout out to Dr. Bennett as well, who was very kind in talking to us and providing his MetSim code for us to integrate. Finally, if you haven't heard already, the director of HEC is retiring this week, Chris Dunn. So I want to give a major shout out to him as well. He's been the director for nearly 20 years at HEC. We've only had 4 directors at HEC since its creation in the 1960s. There's a nice continuity going there as well. He's been a major supporter of the HMS team, allowing us to grow and hire awesome people like Avital, Melissa, and Lauren as well, which wouldn't have been an option in the past. Been very, very supportive. Thank you, Chris. Congratulations on an awesome career. You're going to be missed. I'm very much looking forward to Leah taking up the helm. So everybody say congratulations to Leah Adams on her selection as the next HEC director as well. All right, we are at the end. If you're interested in more information, here's our website, as you're no doubt aware. You can download the latest and greatest beta, which is beta 6, which incorporates all of these methods that we talked about here. We're getting close to a final release for version 4.12, so that is imminent. It is coming soon. If you're interested in getting added to our email list, hit us up here if you aren't already on it. Send us an email, put email list in the subject, and we'll get it taken care of for you as well. Kick it back over to Avital for emceeing the Q&A session, if there are any.
Yeah, like I said in the chat, we have about 15 minutes for Q&A, and we only had 1 question roll in. So if you've been holding on to a question, now is the time to put it in the chat, and we have time to get to it. I'm also going to drop a link in the chat if you are interested in being added to our email list. There's information there in case someone forwarded you this invite today. All right, we had 1 question about the calibration app aid, and I posted a link to HEC's GitHub. Mike, I don't know if you want to expand at all, but you can clone that repository and access the calibration aid that way.
Yeah, I should say, so this, Tommy wrote this to be used for a specific project. Doesn't mean that it can't be used for other things as well. Be aware that there may be some slight hiccups in how other people write out their data, but I've personally used it to assess goodness of fit with other models like HEC-RAS and some of the time series they output, so it is flexible and allows you to do cool stuff. The really, really nice thing is that you can narrow the time window to something different than the simulation that you actually compute within HMS or within RAS or whatever else. And you can also change the time step over which you would like to compute statistics. 2 very, very nice features.
All right, we had 2 more questions roll in. Before I move on, I want to clarify, if you are grabbing the calibration aid, you can download an EXE also. Greg asked, what is the performance of a simplified snow method like temperature index with basic MET inputs versus a more complex snow method with some of the new MET processes?
I know that guy. That's a loaded question. That's a really, really good question, though, and something that we would definitely like to assess. And we actually have work in progress to do that. This is a common misconception that Just because you have more terms, it's always better. We're not necessarily convinced of that, right? So we would like to take temperature index and other simplified methods as far as they possibly can go before they break. But we would like to assess them and deduce their relative accuracies or inaccuracies, if you want to put that way, when compared against these higher order modeling methods that are using simplified meteorologic inputs, right, especially in future climate scenarios that is of particular interest.
All right, next question from Roger, $1 million question. Any idea when HMS version 4.12 will be officially released?
I would say it's imminent, weeks most. We're nearly there. Beta 6 is very, very close. Please help us out. That's Beta 6. Let us know if you run into any troubles.
All right, next question from Michelle. For temperature disaggregation, is it possible to change the hours of daily low and high temperatures?
Throughout the simulation time period, currently you set what the high temperature, the time of high temperature is, and the daily low will change throughout the year. So over the summer, the sun rises earlier in the day, so you get a time of low temperature earlier in the day than it is in the winter, at least in the northern hemisphere. That will work the other way if you wanted to use this in the southern hemisphere. So the low changes throughout the day, but the high temperature stays the same. We could implement parameter value patterns for that one as well. If you're interested, hit us up and we can talk about that.
All right, next we have a comment from Sonia. The hybrid method for snowmelt is pretty impressive and doesn't seem to have a huge data lift. Thank you for that. We like hearing that. And a question from Alan, how common is it to compute peak flow frequency on hydrologic model results? And are there some examples of projects that have used this approach?
We do that quite a bit, actually. It's nice to incorporate as much information as you can possibly get, but also have uniform data, right? You want it to be homogeneous. If something has drastically changed within your watershed, arguably one of the best ways to make that homogeneous is to use current conditions or whatever conditions you're specifically looking at and simulate it again. So we do this quite a bit, to be honest. The two examples that we linked earlier as tutorial guides are some examples of using this approach. There are numerous others that we have on our website as well. I'm sure that there's other folks that can chime in there too and offer their inputs. Make me a liar. Somebody's got to use this. Come on now. Lauren, Melissa, you guys ever done this?
Well, we couldn't until now with our new methods.
Bravo.
Yeah, I've definitely used it to kind of do something that, kind of like the example you were mentioning, if there's been changes in the watershed, the best way to kind of take out those non-stationarities, I guess, or like changes in the watershed was using an HMS model to boost our peak flow frequency estimates.
I'll pause in the hopes that someone asks another question. If you do have to drop off, thank you for joining us. Our next quarterly webinar will be in June. And like I said, this video will be posted on our YouTube channel within a few days. Okay, we got a question from Melanie. Is there any chance the future HMS versions will include runoff water temperature forecasts?
We've definitely had some interest in water quality. Simulation capabilities within HMS, definitely in their infancy. Others would be better suited to answer this question for sure, like Natasha. No, she's not on right now, but I'll leave that one open if others on the HMS team have input.
All right, another question from Greg. Have you compared or considered comparing the simplified methods forced with reanalysis data to the other data imputed by a reanalysis data set?
So comparing the output from the simplified methods versus other reanalysis data? Yeah. The time period matters over which we're comparing. I've mostly been focused on observations up to this point, but I have looked at them a little bit. A lot of the reanalysis data is doing something similar to what we're doing, where we're assuming something else, or in the case of something like MetSim, where they actually do simulate through a couple of iterations some of the other forcings based upon precip and temperature. If you have examples, hit me up. I got some from Panama as well, which is really cool, and I could share those if you're interested.
All right, question from Davis. Do these disaggregation tools augment or work alongside the storm transposition work that Greg has presented on before? Good question.
Remember being pumped and saying we should do this, and Greg had me slow down a bit on that one. For right now, let's keep those separated. But we could investigate that in the future, possibly to build a bigger storm catalog. AORC offers a really, really nice period of record for that specific purpose, though. Even though we talked about it as being somewhat limited in that you can't simulate old events, older than 1979, it does offer a very nice length for computing a storm catalog for use with the SST methods, SST method. I should say, if you do have additional questions that you think of later on, feel free to email us, hit us up. We're always willing to discuss any of these new features. And specifically, if you guys are testing these things out, let me know what works. Let me know what doesn't work. I'd like to hear from you. And also what you think about our new documentation too. Very interested to hear about that and any recommendations for improvements you can suggest.
All right, I think we're going to give everyone 8 minutes back. Thank you for joining us today. And like I said, our next quarterly webinar will be in June. Please be on the lookout for that email. And we'll see you then. Have a great rest of your day.
Thank you.
Thank you.